When a power analyzer is used for high-precision power measurements with currents of more than 50 amps, then almost always current sensors come into play. At the same time, the inductive behavior of current sensors always causes a phase shift between voltage and current when measuring AC power at higher frequencies. Ignoring this can have a big effect on your measurement results. Find out in this video how much impact phase shift can have on your measurement and how easy it is to compensate it with the right tools. Improving power efficiency of motor drive systems for electric vehicles or DC-DC power supplies means a continuous increase of switching speeds in the inverters. The good news is that phase shift is nothing you have to worry about too much if the frequencies in your switching device stay below 10 kHz. The bad news is that you have to consider harmonics in power analysis because high-speed switching systems generate high-order harmonics. So just looking at the switching frequency itself is not enough. To show you the effect that phase shift has on your measurement results, we have done a comparison doing the same measurement once with phase shift correction and once without. For our comparison, we have chosen one of the most common inverter setups, one DC phase going into an inverter and 3 AC phases on the output side. Looking at the measured inverter efficiency and the loss of power in the inverter, you can see the positive impact phase shift correction has on your measurement results as the measured loss is lower and the measured efficiency is higher. Utilizing phase shift correction and reducing the error caused by this physical phenomenon of phase shift increases the output of an inverter even at this low switching frequency by 0.1 to 0.15%. While this value doesn't look like a lot, every engineer working on improving the efficiency of inverters will tell you that this is a significant number. It's easy to imagine the difference in efficiency results when performing the same measurement with an inverter that runs on higher switching frequencies. So how does phase shift correction work? Phase shift correction in power analysis is like dancing a tango. It takes two, the power analyzer supporting the function, as well as a suitable sensor with a known phase delay. If one of them is missing, well, just imagine that tango. A good way to explain how phase shift correction works in the power analyzer software is by comparing it to the desq function of an oscilloscope. If two different signals arrive at the oscilloscope at different times due to the latencies, then the desq function lets you align those signals by compensating the latency with a fixed time value. When you enter this phase shift correction value in a power analyzer like Hioki's PW6001, then you basically do the same thing because phase shift is essentially a time delay between current and voltage. As an example, here is how this delay looks for a Hioki CT68 series current sensor. The time delay is shown in nanoseconds against the frequency. Of course, 100 nanoseconds delay at 100 Hz doesn't have the same impact as 100 nanoseconds delay at 1 MHz. This becomes clear when translating the above time delay into phase delay values described in degrees. To make things as straightforward like in this case, of course you need a current sensor where the time delay is the same regardless of the frequency. With Hioki current sensors like the CT68 series, this is the case, so coming back to the desq function, you only need one value to compensate the phase shift of the sensor. This is one of the things that makes Hioki sensors special, but it's not standard for current sensors currently on the market. Here is what would happen with a typical current sensor. A sensor where the time delay values are different depending on the frequency will make the phase shift compensation in a power analyzer much more difficult. Because which value do you use as your desq parameter? Another thing that makes Hioki current sensor special is that for the phase delay it is not relevant where your wire core is located within the sensor when you make the measurement. The reason why you can only see one single line in the chart is because the phase delay curves for all 5 measurement positions are the same. Again, this is not a standard feature for current sensors currently on the market. Typically, the position of the wire core within the sensor looks more like this. As you can see, there is no phase shift compensation without a power analyzer to support the feature. But as you can also see, only the combination of power analyzer and suitable current sensor allows you to perform a proper phase shift compensation in your measurements. Hioki has been concentrating on making sensors for power measurement for many years, so time delay characteristics have always been a focus point for Hioki's engineers. At the same time, current sensors from other manufacturers are typically only designed for accurate DC current sensing, where phase delay characteristics are less important. This makes Hioki power analyzers together with Hioki current sensors the perfect combination for your wideband power analysis applications from DC to high frequency. Because like with the tango, it takes two. Thanks for watching.